Hello, good morning, good evening, everybody, wherever you might be. It is my great honor and pleasure to introduce my friend and colleague ANDRZEJ SITARZ, who will flow with the Ricci in a non-commutative way. It's all yours, take it away.
Okay, thank you so much, Piotr. It's a great pleasure to give a talk here in this famous still North Atlantic seminar.
I'm sorry, I'm South Atlantic now.
You're South Atlantic, or not, or South Atlantic or Pacific rather.
No, Atlantic.
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 Okay, good. Anyway, so with one exception, we are North Atlantic. And I want to give a talk which is more conceptual and about some ideas. Uh, this is on a work in progress. So still there are more questions than answers, but I think this might be a good idea to give talks which pose some questions. Anyway, this is a joint work. So this is something which is project I started with three master students and well, we're progressing and I will just tell you briefly the idea about what is a non-commutative Ricci flow. Oh, sort of concept, based on uh, some ideas linked, of course, with spectral triples. So let me just, yeah. So the first thing, I need to explain what is a Ricci flow, just in a very few words. So this setup is very standard. So if you take a Riemannian manifold, well, you can make it compact, but it could be also locally compact, doesn't really matter. But you take a Riemannian manifold, smooth Riemannian manifolds, and then you have a metric, which is usually defined in the standard way as a map over the functions, C infinity functions from the bimodule. This is actually a commutative, so left and right multiplication is the same. So the bimodule of vector fields over the manifold. So the tensor product of vector fields with themselves over the functions into the functions. So this is the standard definition of the metric. Then you build Levi-Civita connection, which is a torsion-free, compatible with the metric connection. Then you build Riemann curvature tensor, which is just defined here using this notion, using the Levi-Civita connection. So this is the Riemann tensor, which, it's not obvious, but it's a tensor. And then you build further geometric quantities. The first is the Ricci curvature. So Ricci tensor is a two-tensor symmetric tensor, the same type as metric, which is a trace of the Riemann tensor. And then, of course, finally, you can build a function, which is just the trace of the Ricci tensor, so the contraction of the Ricci tensor with the metric, which is the scalar of curvature. So this is the basic setup, basic things that we do with Riemannian manifolds when we study learning and study exploring Riemannian geometry. Now, what is the next step? The next step is just to define a flow, which means basically a heat type equation, which links the metric with the Ricci tensor depending on the metric. So assuming you have and here, of course, come all the details. So you assume you have a one parameter family of Riemannian metrics, which is smooth in T. So T starts at 0. So this might be an interval. It might be from minus infinity to infinity. I will briefly mention, the problems related to that. And then, well, you just want the equation that the partial derivative or the derivative of with respect to T of the metric is proportional. The proportional constant here is -2, is proportional to the Ricci tensor evaluated at the metric at point T. So, first of all, of course, what people studied, what is this type of equation? It is sort of a heat type equation, but it's highly nonlinear. Why? Because, of course, the right-hand side, Ricci tensor, is highly nonlinear tensor depending on a metric. So it's a highly nonlinear equation for the metric, which, however, has very, very nice properties. I mean, it's been discovered in mathematical terms or proposed in mathematical terms not so long ago. I mean, the Richard Hamilton in 82, this is something like, well, 44 years ago, if I'm correct. Yeah. So, Tomek, you have a question? You raised hand.
Yes, I have a question. Consider a flat Riemannian metric
Yeah.
and a small perturbation. Then you can linearize this equation.
Yeah,
And
it could
the
be
linearization
linearized,
is,
yes.
and then you obtain the heat equation.
It's a little bit more complicated than heat.
More
You will
complicated.
see it. You will see it. I will show in one example. I will show how the actually there will be a non-commutative example, but the linear terms are like commutative ones. So I will show how it looks like. It's a little bit more complicated, but it's heat type. Heat type. So on the
Heat
right
type,
hand
okay.
side, this is something like a Laplace. It could be something more than Laplace, but something like that. Yeah. So
Okay, thank
this
you.
is the relation. Yeah, you're right. The linearized things is like that. Now, then, I mean, it started. So the applications and the topic of Ricci flow is huge. And the application of the Ricci flow, I mean, just, started to be abandoned, I mean, since then. And basically, I mean, some of the very nice mathematical results like the Perelman's result and geometrization and all the other things, I mean, started to be linked, I mean, started to be obtained using some Ricci flow techniques. Now, the intuition is something that I mean, this is like the equation for the metric. So you change the metric tensor, and this is the point, I mean, in which direction you change it. And this is the direction, I mean, this is the intuition. You're somehow like smoothing out. It doesn't mean that you are escaping some singularities. We'll also see it in some examples, I mean, how it looks like. Now, of course, I mean, if you have an equation of the type, basically a nonlinear equation, what are the typical problem is the existence of solutions. And of course, the short-time existence, I mean, assured and uniqueness. And this is for smooth metric initial conditions. I mean, this is assured. But of course, the typical problem is whether you can prolong the solution. So if the solution, I mean, can be prolonged, so first to infinity. So if you have this intuition, or you have the sort of interpretation of this parameter t as time, can you interpret it? Can you move it to infinity in time? So is the evolution, I mean, going to infinity, or does it, I mean, encounter some singularity? And we'll see actually, I mean, that this might be the case. And also, the other way around. So can the evolution be extended back, something like backwards, to minus infinity? Tomek?
Yes, so I'm not sure if it's a good point to ask this question, but since you are a physicist also, so you probably could explain. So you started with the positive, definite Riemannian metric.
Yeah.
What happens when the signature is Lorentzian?
Oh,
what are properties of this equation, solutions to this equation?
I don't know. Honestly, I don't know. I can tell you one thing, that of course, there's a huge sort of research activity related to the applications of Ricci flow in gravity. And this is both in gravity, quantum field theory, and all these things, and perturbative gravity. And there are some recent results, I mean, that some of my colleagues in physics are quite excited about, showing some results, which are based on the Ricci flow. But I mean, I don't know anything about, how are the properties of the equation when you move to the Lorentzian signature. But of course, technically, I mean, the equation could be, so to say, postulated also for that. Piotr circled.
Yeah, I have a question about your date.
Yep.
Are you sure it's 1982?
Yes, I think so. That's
I thought of Hamilton more as 19th century guy.
That's not the same Hamilton.
Ah,
Richard.
my goodness. I'm so
Richard.
sorry.
That's not the same Hamilton, I think. I mean, this
Not
is, you know,
William Rowan Hamilton.
Okay.
yeah.
I think that this Hamilton is still alive. Yes, am I right?
The Richard Hamilton, I think, yes. Yeah.
I have
I mean,
follow-up question
you know, Ricci flow is really recent. It's not 19th century.
Mhm.
It's
Yeah,
20th
sure.
century discovery.
I
Yeah.
have a follow-up question, if I could.
Yep.
So, since you mentioned that some physicists are interested in this Ricci flow in the context of gravity and also in the context of quantum field theory. So,
Yep.
regarding gravity, I can guess that what is evolving is the metric, but regarding quantum field theory, I don't have any idea what is evolving.
Now, this is about, you know, some approach to quantum gravity. So this is still metric,
Ah,
but approach to quantum field theory with the metric. So you know, I mean, for example, I mean, there are simulations of quantum gravity when you treat gravity, I mean, the metric, or treat the length as a field, and you quantize it, and you look at it, and some techniques with the Ricci flow, which I just, you know, had. I mean, there are some recent results, I mean, are so sort of promising, you know. But
so this is
again,
a
I mean, I can give
direction.
you the references later on, but
Okay, so this is the direction of quantum gravity, yes,
yeah. This is direction
or
of
that's
quantum.
semi-classical,
No, this is
meaning.
direction of quantum. Well, I think, I mean, they're using it in a perturbative regime, so that's
Uh-huh.
something like that. But
Okay.
I mean, this is just, sort of a side remark that Ricci
Okay.
flow is in many places. Anyway,
Mhm.
so some examples, and so just before one moves to something which is non-commutative, Tomek.
Short question following up, Adam. So, what is the parameter T in physical applications?
Oh, okay. So in physical applications, I mean, there could be, so could be several interpretations. I mean, you can just look at it as some sort of independent evolution parameter, but there's also, you know, some links to like something like temperature, so thermodynamic interpretation of that.
Mhm.
And this is like, you know, cooling or heating up gravity. Okay, whatever. I'm repeating some keywords, but that's okay. So
Thank
if you look at this Ricci flow, I mean, you can look at some very basic examples, and just, you know, having a look at this very basic examples give you some idea what it is. So there are some properties with scaling. So if you scale the metric, scale the parameter, then if g of t solves the Ricci flow, so if you rescale the metric and rescale the parameter, so it's thus the rescale thing also is the solution. Now, and there are special cases, and those special cases are, you know, those that are quite interesting. I mean, there are Einstein manifolds. So Einstein manifolds are manifolds where the Ricci tensor is proportional to the metric tensor. And typical examples, I mean, would be, well, for example, the torus, flat torus, I mean, the proportionality constant is 0. I mean, but if you look at it, I mean, the flat torus, and then you can look up, I mean, what happens if you rescale the manifold. So, I mean, for example, for the round sphere, you take the round sphere, you take the round metric, and you just change the radius and make the radius dependent on this parameter t, and look what is the solution for the Ricci flow for this r of t. And for the spheres, and this is presented here for the arbitrary sphere in the arbitrary dimension as n. I mean, of course, n equals 1 is sort of trivial, because then the Ricci tensor vanishes. But anyway, I mean, if you just make this radius of the sphere depending, I mean, on this parameter t, then the equation is very simple, and then the solution, I mean, is something that actually is quite interesting. I mean, you can find an explicit solution, and the solution is here written. This is r of t square root r0 minus some parameter depending on the dimension times t, which means that in a finite time, you reach singularity. So it actually, I mean, is shrinking. So, you know, I mean, those are just exemplary solutions. On a flat tori, I mean, there's nothing special that you cannot really imagine a flat tori remains flat and the radius, so if you expand or want to shrink the torus and look whether this is the solution of the Ricci flow, then the only solution is that rho, which is this parameter for the size of the torus, is constant, so nothing changes. Tomek, you still have a raised hand. Is this? But I think this is the remnant of what was.
No. I have a question.
Yeah.
I have a question about the scaling. So, is this the only transformation which?
No. That's an example of a transformation that holds. I don't know whether there are probably more. I mean, I don't want. You see, I mean, this is just some basic properties, and the question is, I mean, whether these basic properties would hold when you go to certain generalization. So this, I mean, I'm showing you this only just, for a very simple reason, because I mean, when you go non-commutative, I mean, there are very nice examples, and there are very nice examples of things that are non-commutative tori and non-commutative spheres. So looking up these examples in a classical realm, I mean, and then, I mean, would make sense, to compare them later to the non-commutative one. Okay, if you have, so now assuming that you have an evolution of the metric, which goes according to the Ricci flow, so according to this equation, now you can ask, I mean, about what other geometric quantities, how do they vary? And these are, again, just examples. So the first example is how the volume element, so volume element, if you have a Riemannian metric, I mean, is basically something like a square root of G, how the volume element varies.
Sorry, Andrzej, this mu G is the volume element, right?
Yeah.
Okay.
Yeah, this mu G, that's what I thought. Mu G is a volume element. So how the volume element evolves when the metric evolves according to the Ricci flow. And the answer is very simple. It's just proportional to itself, with the proportionality constant being the scalar of curvature. Again, how the scalar curvature evolves, and this is something, which, well, roughly, I mean, remember, I mean, had it not been this term, I mean, twice the square of the Ricci tensor, I mean, it would be basically like a heat equation, right? So this is how this is sort of parallel to the heat equation. And also, you can write the equation for the Ricci tensor, which is even more complicated. So the Ricci tensor, I mean, you have the Ricci tensor, so the Laplacian acting on the Ricci tensor, but then you have the contractions of the Ricci tensor, and you have the contraction of the Ricci tensor with the Riemann tensor. So very complicated. But anyway, I mean, this is something that, I mean, could be derived.
May I have a question at this point?
Yep. Sure.
So what is special about all these equations? It is the fact that if you take the derivative of any of these invariants, these tensors, the right-hand side contains other tensors. Not only this you are differentiating.
Exactly.
So my question is, can you build up a combination of tensors, of the curvature tensor of this Riemann metric, to get something which, some object which evolves according to some rule that the derivative of it is expressed by some natural operator applied to this. How to cancel, for instance?
I don't know. I mean, as you can see, I mean, for the scalar, so for the volume element, you get a scalar curvature. For the scalar curvature, you get the Ricci tensor. For the Ricci tensor, you get the Riemann tensor. I think, when you go for the Riemann tensor, I don't remember, I mean, but there must be an equation for the Riemann tensor. And I think I would suppose that for the Riemann tensor, I mean, you just get only Riemann tensor on the right-hand side.
Without Laplacian applied to something?
Sorry?
Without even Laplacian applied to something?
No, with Laplacian, but I mean...
with Laplacian, okay.
Yeah. There will be Laplacian and some contractions, I think, yeah.
Okay. So what about the Weil tensor?
I don't know.
Conformal Weil tensor.
I don't know. I can give you a reference when all these formulas are, well, I wouldn't say all the formulas because I mean, probably not all, but they are nicely compiled. But I don't remember. I mean, I've just, written the first three, which are the easiest, and one of them will actually be used.
Yeah, I would be grateful. Thank you.
Okay. So, I mean, there are, of course, other special cases. So I've mentioned, the case of Einstein manifolds, in particular spheres and the tori. But of course, the two-dimensional case is also very special. And in two-dimension, I mean, the Ricci flow is very easy. And the Ricci flow in two dimensions, I mean, is just, the derivative of metric is just the scalar of curvature times the metric with minus sign. And then, I mean, there's also nice thing, namely, I mean, as a consequence, what one can do, I mean, using, of course, the Gauss-Bonnet theorem, so for the compact manifold, one can just show that the volume, because, I mean, if the metric changes, I mean, the volume element changes, and we know how it changes, but also the total volume of the manifold will change. And the change of the volume of the manifold is then proportional to the Euler characteristic. So, which means, and this is quite interesting, that basically, I mean, since when you have a compact manifold and then, the Euler characteristic is just a number, I mean, what you basically get, that depending on the Euler characteristic, volume grows linearly or shrinks linearly. So this is something like that, which brings us to the point, and that was one of the motivation, is to consider modifications of the Ricci flow. So there's been some proposed modifications of the Ricci flow, which is called just like, I will just flash this side, normalized Ricci flow. And the idea, I mean, the concept behind the normalized Ricci flow, so just modification of the Ricci flow, is just to keep the volume constant. So this is the flow where you modify the Ricci flow equation. Basically, you modify it like this is like the first part is the usual Ricci flow, but you add something. You add something which is something proportional to the metric, and on the right-hand side, and this constant which gives you this additional term proportional to the metric is so-called average scalar curvature. And with that, you can make sure that the volume is preserved. And this is just, this short.
Ali, you have a question. Go ahead.
Yeah.
Ali? Okay, so then I have a question.
Do you hear me?
Yes. Yeah, I can hear you, but can you show yourself too?
Yes. In the formula of computation of the derivative of the volume for or some other thing in the previous page, are this computation is correspond to a t equal to 0, or it's true for all t? Could you please bring the previous page? No, not the previous one. For example, in this, my question is that are these formula counted at t equal to 0, or it's for all t?
That's for all t if the right-hand side is this g of t. Yeah.
Yes. So I think that there are something strange. In the next slide, when you wrote the Euler characteristic, in the right-hand side there is no any t. Could you please, yes, -4 Euler characteristic of the manifold. So it's independent of t.
Okay, so there was something, some noise in the background. Yes, because I mean this is the total volume of the manifold. So the total volume of the manifold, and this is basically, I mean, if you take it, so the total volume of the manifold, when you change it with respect to t, so this is the derivative, is constant. So which means that the volume, I mean, is linear in t.
Yes, but it's not obvious because when we change the metric, so the volume form is changed. I think at the first glance, it's not obvious that the volume is linear in t. So as a particular case, when we involve with a manifold with a zero Euler characteristic, for example, torus,
Yep.
we get zero. And so my question is that in the case of torus, is it true to say that torus or every other manifold with a zero Euler characteristic, is it true to say that all resulting GT, they are isometric metric?
That I don't know.
Why?
Because
No, in general.
no.
Because there is no an obvious abstraction, because in a zero Euler characteristic, the volume is constant, so it would be reasonable that we expect that the matrix, the nature of matrix doesn't change. So
Yeah, but I mean, this is the total volume of the
Volume.
manifold. So
Yes,
this
yes,
is, the total
no.
volume of the manifold is
the
constant, but
total volume is constant.
the changes inside, I mean, could be different, I think.
Could be different, but it's a motivation to ask this question. In the case of the zero Euler characteristic, is
Yep.
it always true that the metric, all GT are isometric?
No, I don't know.
No.
I wouldn't think so, but I don't know.
I think that those
Thank you.
previous examples somehow addresses those questions, yes, since
Which
you mentioned
example,
the
Adam?
flat torus, yes. So
Yeah, I mean for the flat torus, I mean the flat torus, I mean when you look for the flat torus with the, for example, the radii of the tora inside, I mean changing with time, I mean of course then you get only constant. So this is like that. But I don't know. I mean if you look, for example, at torus embedded in space, I mean then the curvature is
not
still
constant.
is locally different, and you can modify
Yes.
it.
Yes.
Yeah.
Okay. Thank you.
Okay. So
and
this
Adam,
is the
wait, I'm a bit confused by your normalized Ricci flow. So you are saying that it is defined by this equation, right?
yeah.
But you use the same notation.
What do you mean same notation?
Well, before for the usual Ricci tensor, you also use these three letters RIC.
no. You have this additional term.
There's this additional
Small
term.
r.
I mean in the usual Ricci flow,
Small r.
there's no
This
this.
term.
Yeah, exactly. This term is not present.
Okay, so you add this average thing. That's
Yes.
fine. That's fine. No, you see, for me, what is confusing is the notation, because I believe you use exactly the same notation for your modified, normalized Ricci flow as you used for the usual one.
No, Piotr. Ricci is Ricci tensor. It's not Ricci flow.
It's just R. Okay.
Ricci is Ricci means the Ricci tensor.
Yes. So Ricci tensor or normalized Ricci tensor?
No, Ricci tensor. Just the Ricci tensor.
So Ricci tensor is the same, and you modify the equation, and the Ricci flow
The
is
equation
the
is modified. So
equation.
Okay, because
normalized
the
Ricci
flow. Okay.
The flow is evolution.
I
Yes.
got me confused.
It's the flow which is
Different
normalized,
equation.
not the Ricci
So it
which
has
is
different
normalized.
solutions. So the flow is about the evolution of G.
Yeah.
Okay.
Yeah.
Thank you. I'm glad I asked because I got confused.
Very good. So, okay, I mean the things that are drawn still. Okay, yeah. So just, very, very short slide. I mean, saying which is a huge topic, probably for a full semester lecture. I mean, what are the applications? I will not just, that there are many, many, many applications of the Ricci flow, and still an active area of research. But what I want to just go to is the Ricci flow in noncommutative geometry. So how to define Ricci flow in noncommutative geometry? And there's been several approaches, several ideas, and the point is the following. So first, what is the metric? And the second, what is the Ricci tensor? And both things, I mean, have well, only partial answers, I mean, for all the things. And there's been approached by Sergio Vaccaro for star products, I mean, based on just the usual differential geometry and some frames and all this, I mean, for the star product. There's been approach also by spectral triples, which I will briefly say something about, which is based on the ideas, I mean, how the eigenvalues of the Dirac operator change under the Ricci flow. Generally, I mean, one can propose things like abstractly, something like, well, we know that the volume element or the volume, I mean, changes something like, I mean, we had this equation, right? There was this d by dt volume element, I mean, is the integral of the scalar of curvature. So, for example, having the nice concept of what is the volume of a spectral tuple so you take a spectral tuple with nicely defined Dirac operator, which is finitely summable and so on and so forth. So you can define what is the volume. You can define what is the, more or less, what is this R of D, so the something like the functional, which gives you the integrated scalar curvature. And you can just, say, okay, something.
So the Einstein action, right?
Yes, exactly. Einstein-Hilbert action. And then you can just say, something that, so flow, so the dependence on time of the Dirac operators for the spectral triple satisfies the Ricci flow if this is satisfied. But this is very, very unsatisfactory because this is just one scalar equation. So now first brief review of what's been done. So the first idea was, okay, let's look at the Dirac operator. And let's look at classically, and that's been done, I mean, in the past by Bourguignon-Gauduchon in a very nice paper written. There were the times that they were still writing in French and still in communication in mathematical physics. I mean, things were published in French. So the title and the full paper is in French, Spinner, Opérateur de Dirac and Variation des métriques. And basically the idea is, I mean, just to answer a very simple question. So imagine you have a very, very simple modification of the metric, like it's on the screen. So GT is just G plus T times H, where H is some tensor. So something like a small perturbation of the metric, because I mean you'll be looking at it at t0. So at t0 you have the original metric and you slightly linearly change it. And then there's a question, how does the Dirac operator change? And basically the answer is there. And the answer is not very simple, because if you look at the Dirac operator, so the Dirac operator, I mean, how you construct the Dirac operator, you take so you have the spinor bundle, you have the Levi-Civita connection. So first, when you change the metric, the Levi-Civita connection changes, of course, because you change the metric and Levi-Civita connection is compatible with the metric. So then you lift it to the spinor bundle, and then you use Clifford multiplication. But the Clifford multiplication also changes because, I mean, Clifford multiplication also depends on the metric. So there's a huge complicated formula. And basically, the Bourguignon-Gauduchon formula tells you that if you have a smooth spinor psi, so you take a section of the spinor bundle, which is smooth, and you want to evaluate, so you have a family of Dirac operators that are constructed for the metric GT, and this metric GT is this G plus TH, and you take the derivative.
Sorry, Andrzej, when you say G plus TH, this G itself, does it depend on T or not?
No. G is original metric, and you take a small, so to say, well, because you look at T0, you take a linear perturbation. Okay. So this is like really take the metric, which is GT is G plus T times H.
Before you use the notation G subscript 0. So for
me, but so here, I mean, there's no this G0, but it is exactly like that. Yeah. So, and then you look, I mean, what happens when you take the derivative with respect to t at t0? So basically, this is again an operator acting on spinors, and how does it act on a spinor psi? And the answer, I mean, is using orthonormal frame. So if you have an orthonormal frame, this is with respect to the metric, this G0, so G, and you know this H, then you can basically, it's computable. So it's computable how this derivative at point T0 acts on this spinor psi. Now, of course, you can apply it to the Ricci flow. So if you take H to be Ricci of G, so this somehow models, the Ricci flow, because this is like derivative at T0 should be the Ricci tensor. This is the proportionality. Then you can just, apply it and say, okay, this how the Dirac operator changes, or the derivative of the Dirac operator looks like at T0.
I have a quick question.
Yep.
About this divergence. So divergence is defined for a vector field, and here H is a tensor, yes? So
yeah, this is for the tensor. So this is like the nabla I Hij. So it gives you, so this is contracting two indices of the covariant derivative with the tensor. There remains one index, so it is a vector, is like a vector, and then you use Clifford multiplication.
Okay.
So that's, I would not go into the detail. I mean, there's a divergence defined on these tensors.
Andrzej,
Anyway.
can you hear me? Andrzej?
Ludwig?
Okay.
Yes.
So, okay. Actually, Bourguignon-Godeschon cites my paper in which I noted, and also people before me already said this, it's not only that the metric changes, but also spin or field depends on the metric. So in principle, this equation is, I mean, it's easier to write for an equation for an operator acting on spinors, rather than putting this equation also spin or psi explicitly here, okay? So it is because also this depends on the metric. So it is an additional complication, which I don't know if it's properly, how to say, represented by this equation. If you write it without psi, then it makes sense more. Because the Dirac operator is kind of vector-like operator, so you could, it's not a spinorial type operator, it's a vector type operator, so you can write it dependence, measure its dependence on G, on the metric. While spinor
the measure is also dependent.
It's a more complicated, deeper question, which is another issue, okay.
Yeah.
Okay.
So, I mean, I will mention that, this is a paper that's been, I think, in the 90s, if I'm correct, or early 90s, or even
98, 88, I think.
Or around 90s, or 80 something, yeah. And there's been some more recent papers which do some computations which slightly differs from that. So that's okay. I mean, but that's also the question of the notation. But anyway, okay. I mean, the bottom line here is it's very nice, but still it doesn't tell you very much about the, I mean, okay, once you know how the metric changes with the Ricci flow, you can compute the right-hand side and you can see what is this derivative at T0. But if you ask the question how for example, I mean, the Dirac operator, how the eigenvalues, for example, of the Dirac operator change, this is basically out of question. And this doesn't tell you the sort of implicit equation, I mean, linking Dirac operator with something which is Dirac operator. Tomek, you have a question?
Yes, I have a follow-up of Ludwig's comment, namely, for me, this equation doesn't make sense because of the fact that changing metric, you're changing a definition of a spinor. Okay, so this is highly incomplete. If you variate the metric, you should variate the representation of the orthogonal group on spinors. So
I mean,
full.
I mean, that's you know what you mean. I mean, you change the Clifford multiplication, exactly.
Yeah, not only
So
Clifford
this is the
multiplication,
representation of the
not only,
vector fields on the
not only.
spinors.
Yeah. So Clifford multiplication is on the level of the Clifford algebra. It's one thing.
Yeah.
But on the level of spinors, you have also the representation of the spin group. Okay, and this also changes because spinors are not defined uniquely. So it's more than dependence on the metric. Because this representation of the spin group can vary. It's a choice. Spinors are defined only up to some choice.
Yes.
So I think this is the serious problem here.
Andrzej,
Yeah.
let me take it really down to earth in the
Ludwig,
physical.
could you please
terms.
show yourself?
Yeah, let's wait. Does it work? Can you see me?
It works.
Yeah, perfect.
Okay, because it was not. Okay, so I mean, for different metrics, even in a point, one and the same point, okay, different metrics. The isometries of these metrics are different subgroups of GLN in dimensions. Okay? They are orthogonal with respect to different metrics. And spinor has to react, must be a representation of a covering of this isometric group, so called spin group.
Yeah.
Which is a different group for different, I mean, you cannot take it the same one, okay, you see. So it's different isometric groups, and well, in principle, you can cover these different groups by different groups, which you call double cover spin. So the space of spinors intrinsically is different for different metrics, you see. They react differently with respect to the isometries, let's say, like that, okay?
So you agree with Tomek, Ludwig?
Absolutely.
Yeah. I think, I mean, I think as far as I remember, I mean, Bourguignon-Goduchon, I mean, take it into account, but I cannot give my head for that because, I mean, this is, as I will mention in other papers, which slightly differ in some aspects. Anyway, so if you look for it, I mean, this is a very nice result, but sort of limited in applications for a very simple reason. You still need to know how the metric changes to see, I mean, how the Dirac operator changes. I mean,
wait, guys, but I'm confused. So have we resolved the question whether this equation makes sense or not? Tomek?
So this equation makes sense if you can vary the metric, the Clifford multiplication, but you are freezing the representation of the spin group somehow. Otherwise, but you have to take the change of this representation into the equation.
Okay.
Okay.
And may I ask you, Andrzej, a stupid question? There's little delta here. What is it?
Little that's the divergence. Divergence applied to tensors.
Okay.
I had a problem with this divergence, but Andrzej explained me
I mean,
that it is understood as a divergence.
For the technical things, you know, if you can read French, you know, Bourguignon-Goduchon paper. Okay. Anyway, so there are some follow-ups. There will be some follow-ups on this. And exactly, I mean, the follow-ups have been studying why I'm mentioning that, because this is, you know, goes into the region where you start see, I mean, how the eigenvalues change. So there's been two papers, one which not been published, I mean, in something like around 20 years ago. So how the eigenvalues, so this is slightly different. It doesn't use spinors, it uses the Laplace operator, so just the scalar things, how the eigenvalues of the Laplacian change under the Ricci flow. And the more recent, Yukiao-Lee, how the eigenvalues of the Dirac operator on compact spin manifolds change under the Ricci flow. And
does it mean that this paper by Luca Fabrizio Di Cerbo was not published?
Not published. I mean, I haven't seen any published versions, so there's only in the archive. I don't know why. Anyway, so basically, I mean, the idea is that, again, so assuming that you have a, say, one parameter family of Dirac operators, well, so something like a flow of the Dirac operator under the Ricci flow of the metric, you have the flow of the eigenspinor, so psi of t is an eigenspinor, and lambda of t is a flow of the eigenvalues, then you can write the equation how for this eigenvalue, how it changes. And basically the equation is that the first derivative of its square is, and a very complicated formula, which again uses this eigenvector, so psi, which is the psi of t, uses the Ricci tensor, uses derivative of Ricci tensor, and so on and so forth. So again, very nice, but absolutely not practical for a very practical reason. I mean, if you have a Ricci flow, just to compute explicitly what is the flow of eigenvectors and eigenvalues is eigenvectors would give you the flow of eigenvalues, and that simply means that this equation is satisfied. You cannot solve this equation. So these are the limitations. So, but there are some special cases, and those papers.
For a moment, could you go back to the slide?
Yep.
This small psi is what?
Oh, sorry, small psi is the big psi. So this is this eigenvector. Yeah.
Okay, but it is normalized. Therefore, I'm a little bit confused about this modulus psi squared at the end of this equation.
Yeah. So, well, it is normalized, yes, but it's normalized
L2
means the integral is 1. But here you have this integral with the square of the Ricci tensor.
Okay, sure.
So that's, it's not that it's normalized at a point.
Yeah.
I mean, it's normalized.
It's like probability density.
Yeah,
sure.
Yeah. Okay, just basically, I mean, those papers and basically the results of Lee are in a way to prove what happens with, say, the first eigenvalue. So if you, for example, if you have a Ricci flow Einstein manifold with non-negative Ricci curvature, square of the eigenvalue of the Dirac operator is non-decreasing. So first eigenvalue or all eigenvalues, that this is non-decreasing. This is the same for the surfaces. So there are some results that can tell you, okay, if there's a Ricci flow, then the eigenvalues or square of the eigenvalues, because eigenvalues could be positive or negative, but the square of eigenvalues must grow. So there are some results that are actually like that. But, again, there's no equation that we can have for the eigenvalues or for the even growth of the eigenvalues of the Dirac operator that would depend only on the Dirac operator. So now let's come.
Andrzej, sorry for that, but since this is the same which Tomek said, and let me just go. So Piotr was asking if the equation makes sense. So if you omit just psi in the equation, it makes sense, because the Dirac operator you can define in terms of Clifford multiplication, gamma representation of elements of the orthogonal base, and so on. So it's kind of tensorial object, okay? So you can write equation for this one, but you should not put psi in this equation. While here in these equations, this psi is very important. I mean, you use the normal. So I'm a little bit. So these are the equations due to this Lee, this guy.
Which one? This one? That's on the one on the screen, or the previous one? You mean this one?
No, in this one, I would just skip psi, and it makes sense for me.
Yeah, I mean, Bourguignon-Godeschon writes this with psi.
Don't be wrong, psi. Okay. But here you have to put psi. Okay. So you keep.
Okay.
One fixed psi, the same Hilbert space on which you act by this operator and things like that, something like that. You ask for the eigenvalues, so you can do this. I mean, but whatever it is, okay.
Okay, let me move to the
Andrzej. Let me make a silly comment. I believe that marking a theorem by Lee, this is extremely ambiguous. I personally know 2 Lees. One is in the audience, another is my brother in China. So I personally know 2 Lees.
Yukiao. I mean, I gave the reference, of course. This is Yukiao, but I understand, if you probably scan the archive, there would be.
I will have like 1 million different Lees.
Yeah. So, okay, let's try. The non-commutative.
May I have a question? So, another question. Could you come back to this last theorem? This formula with it, is there an assumption that psi has multiplicity 1. This lambda, this eigenvalue.
Yeah.
Okay.
I don't remember.
Because
I mean,
otherwise,
I think probably yes.
I couldn't
probably
know how to compute this.
Yeah. You need to
without
assume
assuming that this is a
yeah.
multiplicity of multiplicity 1.
Yeah.
Okay.
Okay, so let me move to the non-commutative stuff and propose what I believe, might be a good formulation of what's a sort of non-commutative Ricci flow. So the setup, let's say you have a non-commutative to torus, and you take the modifications of the Dirac operator. So you take the usual spectral triple of the Dirac operator with the usual flat Dirac operator, which is just written like that. You propose, well, what is the what's called conformally rescaled Dirac operator DH, or I can call it asymmetric or partially conformally rescaled, which is just you rescale only part of the Dirac operator. Now, of course, there are two approaches. So one is that one takes H from the algebra, and then you lose the spectral triple. You get something which is called a twisted spectral triple, but still, nevertheless, could be considered as some sort of geometry. Or you take H from the commutant of the algebra of non-commutative torus, which is something that we advocate with Ludwig for a long time. We've been advocating with Ludwig for a long time, which means that you stay within the realm of spectral triples. So basically, all the tools are still at hand. Now, what was proposed for the non-commutative torus was the idea by Matilde Marcoli, by Bujan and Matilde Marcoli, and that was something like 14 years ago, Ricci flow or non-commutative tutorial, which is basically based on the same idea as this Fabio di Sebra. So like for the Laplacian, they used not the Dirac operator, but the Laplacian. So Laplace operator in terms of k delta k, where delta is just the square sum of squares of derivations, which is the usual, so to say, flat Laplace operator. And then using basically the same equation that was like here, so something like the derivative of the square of the eigenvalue, you can just write that the derivative of the square of the eigenvalue of this Laplace operator, so using this procedure, is somehow like related to the integrated scalar of curvature, which in this case is related to the zeta function associated with this Laplacian. And then what they do, so basically this is the same as the equation at the bottom, but written in non-commutative terms using the zeta function. So they write the equation very nicely. So the d lambda by dt is 2 lambda, tau is the trace on the normalized trace on the non-commutative torus, f is the eigenfunction of this modified Laplacian, r is this scalar of curvature, for which there's a horrible formula depending on this conformal rescaling parameter k. Again, nice formula, but you cannot solve it. Basically it's hopeless because what's on the right-hand side. So first you need to know what's f, and you don't know what's f because that would basically mean solving the eigenvalue eigenstate equation, eigenvalue equation. And the second thing, this r is hugely complicated. So,
Sorry, may I have a question?
Yep.
But if you could go to the previous slide. So once
the
again,
equation at the top is basically
f is defined in this equation. How this f is defined?
F is defined as an eigenfunction for lambda k. So this Laplacian delta k acting on the function f gives you lambda k f. So this is an eigenfunction of this Laplacian.
Okay, and also you have written zeta of f squared, comma 0. And if you take 0, you have just identity, yes? Or
No. Because this you take the value of the zeta function at 0. That's not.
So this is understood as some residue. Sorry.
No, you don't take residue. You take the zeta value of the zeta function.
Okay,
I mean,
okay.
this
So
is
the
based
zeta
on the
okay.
Kontretkov paper, and again,
Okay.
I don't want to go into details. I mean, how the Kontretkov paper works and how the curvature is computed. Just
Okay,
want to
so
say
this formula.
the bottom line, you can have a very nice equation for the evolution of the eigenvalues, which is nice but totally impractical.
So probably this is something like a meromorphic continuation of the
Yeah.
formula which you have written, yes?
Yeah, exactly.
Okay,
And you take
okay.
yeah. That's
So
the
not taken literally, but
structure.
with some
Yeah.
continuation. Okay.
Okay, so you have various approaches which are very nice, deeply, so to say, grounded in differential geometry, computations of curvature and all that, and the Dirac operators, but very unpractical. But fortunately, and this is, the idea and the concept, with Ludwik Dąbrowski and my PhD student, former PhD student, Paweł Zalewski, we discovered a very nice tool, which are spectral functionals. So actually, in a series of papers, we defined 3 functionals, so which is called the metric functional, the Einstein functional, and the torsion functional, which basically in the classical spin geometries give you nothing else but the metric tensor, torsion tensor, if the Dirac operator comes from not from the Levi-Civita connection, but from the connection with a torsion, and the Einstein tensor, which Einstein tensor is a linear combination of the Ricci tensor and the metric tensor with scalar curvature, multiplied by scalar curvature. So now,
yeah, I remember this is very beautiful work, and we one of you guys, probably Ludwig, gave a talk about it, and it's all recorded. So if somebody wants to refresh the memory about it,
yeah,
I invite you to our YouTube channel.
yeah. So using this, we have, you see, you can say, how does it actually compare to the Ricci flow? Because, there's no Ricci tensor. We have only Einstein tensor. But here's the beautiful thing. So if you look at the metric, this is metric functional. So it actually doesn't give you the metric. You evaluated it differential forms, but it gives you the value of the tensor contracted somehow with this differential forms and integrated over the manifold. This is the classical picture. So it gives you basically you can, by localizing these forms, you can get the density. And it has some nice properties. This is the same about the Einstein tensor. So Einstein tensor also gives you something which is integrated. So now it has also very nice properties. The point is why this third functional, so the torsion functional, is needed. Actually, if there is torsion, this no longer is a tensor in the classical case. So if you have a Dirac operator with torsion, then the Einstein functional gives you some extra terms, so it doesn't give you plainly, this Einstein tensor. Now,
Sorry, Andrzej, can you remind me what this means? Vn minus 1?
Oh, this is the volume of the n minus dimensional sphere.
That's what I thought. Okay.
Yeah. So that's for the purpose of the talk, it could be just a constant, doesn't really matter very much. So the beautiful thing is that if you look for the Ricci flow, so assume the metric, assume you have a compact closed manifold, Riemannian manifold, spin manifold, assume you have a Dirac operator, okay, and assume you have a metric which varies according to the Ricci flow. Then it's a very nice result. Then if you look at these functionals, so you can make the metric functional, which then will be depending on this parameter t. And you can also compute, so for fixed one forms u and v, you can compute the Einstein functional, which also will depend on this t. And the link is a very simple and beautiful equation. This 12 is just, comes from, because, there's this 1/6 here, it doesn't really matter that much. But it really is a very nice and simple equation linking 2 spectral functionals. And the proof is just the computation. You can, in the classical case, of course, this is the classical case. So now What is the beauty of that? The beauty of that is that you have a very nice, feasible formula. Yes, thank you very much. Feasible formula which links two spectral functionals in case of Ricci flow, but the spectral functionals could be computed for basically any finitely summable spectral triple with certain properties. So this is applicable to many, many non-commutative geometries. So let's test it. So this is, the very nice test. Can we actually, compute it? As I mentioned, the previous equations for the eigenvalues of Dirac, using this formula by Brian Marcoli, are very nice, but they are basically not computable. Can we compute something here? So let's take the non-commutative 2 torus, and here we use heavily the results obtained in other papers. So the first result is that if you compute the conformally rescaled non-commutative torus, the Dirac operator, take the Dirac operator. So basically, you take the Dirac operator, which is k dk. D is the usual Dirac operator for the non-commutative torus. K taken from the commutant. Then one can compute what's the metric. One can compute that the Einstein functional vanishes identically. So if you postulate that this conformal factor depends on t, you can write the equation. But the equation is sort of stupid. It's 0 equals 0. And why is that? Well, the point is that, and this is, so that would be the next slide, the limitations of this formula. Namely, if you look at it,
sorry to interrupt you, but you see, for me, this is very disturbing when you say that the Ricci flow is an equation. These are two different beings. Either you're an equation or you're a flow. A flow is a mathematical object. It's not an equation.
Yeah, okay, Ricci flow is given by the equation. Yeah. So here, the point is that for this non-commutative torus, or generally for spectral triples, the definition of the one forms includes the Dirac operator. So if the Dirac operator has this conformal factor k, so the one forms include this k square. So you have two one forms, so they both include k squared, so you have k to the fourth. But if you look for the formula for the metric, so I just go a little bit back for the metric, and you look at it, this is the formula for the metric, you have the product of two one forms, and then the Dirac operator to the power minus n. So in the case of two-dimensional torus, it's -2. So you have k to the -4. So this conformal factor cancels. So basically, if you have irrational non-commutative torus, then basically any k of t gives you the Ricci flow. Now,
basically what? Sorry, say it again.
Any k of t, any dependence, any function gives you Ricci flow in this sense, of course. So this is the limitation. So this is the slide about it, limitation of the spectral functional approach. The limitations are that when you consider the Ricci flow itself, the Ricci flow equation itself, it's for the tensors. Here we don't use tensors, we use things that are integrated over the manifold, so basically like densities. And this is the reason that the volume element intervenes, and this is the reason that the conformal factor, actually gets cancelled. So if you look for the commutative torus, the situation is different, because for the commutative torus, you can use different forms. The thing is that by taking, if you rescale the Dirac operator classically by R, then of course this R will be in the one form, but you can rescale this one form also by R, by 1 over R, so just to cancel this factor. You cannot do it in the non-commutative case, because the elements of the algebra, cannot, so to say, cancel sort of the element, this K, which is from the commutant. So the commutant and the algebra are two completely different algebras that the intersection is only complex numbers. So that's the situation of the conformally rescaled non-commutative torus. But there's one more example, which is the asymmetric non-commutative torus, which we somehow thought of with Ludwig many years ago and computed the scalar curvature and the Gauss-Bonnet theorem, which was a very, very difficult task. Then more recently with my PhD student, Diponjit Boze, we computed what is the Einstein tensor. And the Einstein tensor, of course, the metric tensor as well, we showed that the torsion vanishes, so everything is okay. Torsion vanishes. The metric is very nicely presented like that. So this is tau of 1 over k, u1, uv1, u2, v2, where these are the coefficients of the two one forms. And that was absolutely highly non-trivial computation that took quite a while. The Einstein tensor indeed vanishes, as it was conjectured. But anyway, I mean, that's the result. So now, you can take k as a function of t and postulate what is the Ricci flow equation for that. So just you take the d by dt tau of this formula for the metric is 0 because the right-hand side is 0. The Einstein tensor vanishes. And this implies k to be constant, which is just like for the usual torus. Now, 4-dimensional non-commutative torus is a challenge. Why? Because in the 4 dimensions, I mean, we have the explicit, so the conformally rescaled non-commutative 4 torus is a very nice object. We computed that the torsion vanishes. We computed with Ludwig and Paweł what is the metric tensor, so metric functional, what is the Einstein functional, and these are the formulas for both of them. But of course, to find a solution of what might be k of t that satisfy this proposed Ricci flow is something absolutely awkward. What could be done, and this is the idea, that Tomek mentioned, is to linearize it. So just look at the first order perturbation. So you make it linearized. So you take k to be 1 plus some small epsilon h, and you look for the first order in epsilon. And looking at for the first order in epsilon, you can write a very nice equation, which is basically, there's epsilon missing on the right-hand side, but basically it's minus 4 epsilon tau of h dot delta AB is something like 8 tau. Epsilon is missing on the right-hand side, tau of derivatives acting on h, or Laplace operator acting. So this is flat Laplace operator, or thank you, Piotr, acting on h. The point is that
I claim the co-authorship of your work.
Yes, thank you. You're welcome. Now, the point is that if you know the properties of the trace on the non-commutative torus, the right-hand side vanishes. So in the linear approximation, basically any h of t such that the h dot of t is trace 0, has trace 0, so basically has no constant component, is the solution. But of course, this is only first order. So you see, it's not full solution, of course, but the point is that in this approach, you can look at least for the solutions. So you can just look at what is the next order. That's the question. Or if you take a very particular, this is what I'll be looking with students, if you take some particular h related, for example, to Powers-Riffield projection, could it be a solution? So both the equation for this non-commutative Ricci flow and the solutions are feasible, are possible. Next thing, SUQ2. It's sort of fun, but one can also pose the same question for the SUQ2. Why? Because the SUQ2 is a very nice spectral triple, finitely summable. Again, with Ludwig, we've shown that the torsion for this Dirac operator vanishes. so it's torsion free. So one can compute, this is just, the briefly recanting, what is the algebra? The algebra set is generated by BA, A star, and B star satisfying certain rules. There's a very nice spectral triple. There's a very nice Dirac operator, which is three-summable spectral triple, which gives a three-summable spectral triple. And absolutely nice thing is you can compute all the residues. So basically, what was that?
It's also a graph sister algebra for this graph.
It's a graph sister algebra, but that's not highly relevant at this point.
I know, but I just couldn't resist it.
Yeah, you couldn't resist. But the thing is, one can easily compute at least some of these functions. So for example, and this is based on the result on a paper some time ago with Bruno Jochum and Cyril Levy, when we computed, a lot of these functionals and spectral action and basically what is the differential algebra generated by this D and all that with certain rules. And then one can compute what is the metric, for example. So if you take the differential forms like A star dA, then the metric is evaluated on this, so to say, this form with itself, it's 2. If you take A dA star, it's also 2. They are just numbers, but these numbers are computed quite nicely. Interesting thing is if you have anywhere at some point B, so one of these generators B or DB or B star or DB star, then the metric vanishes. So it's highly degenerate metric. It's not like in the classical case. The metric is in a way highly degenerate. Tomek?
Yeah, so in your first examples of functionals, your functionals were defined on V and W being what?
One forms.
One forms. Okay.
One forms.
Okay.
So one forms in the space of one form, so in the bimodule one forms generated by the Dirac operator D. So this is basically the commutator D with something. Yeah. And then you span a bimodule over that. Yeah. So this is a highly degenerate metric. So if you go, for example, and compute the metric for even simple thing, which is just dA star, you can do it, is again 2. No problem. This is easily. And then you can amuse yourself and compute the Einstein functional, which is doable, a little bit tedious, but doable, using all the techniques. So this is, heavily using the techniques that were developed first in the paper on the index computation, local index computation for the SEQ2, and then the paper with Bruno Jochum, when we computed a lot of spectral action functionals. And then
I have a question.
Yep.
How do you interpret the fact that if you substitute naively into this formula Q equal to 1, which is like a commutative case, you get some singularity?
I was just about to comment on that this is a peculiar thing. This is it is highly degenerate. I absolutely agree. But this is something, if you look at this paper with Bruno Jochum, that's what we also observe. There's a lot of formulas when those things appear, like there's those factors 1 over 1 minus q square. So it simply means that the metric in this sense is highly degenerate. Because the algebra, is in a way highly degenerate. So for example, this is something which is absolutely not obvious, but if you look for the relations in the differential algebra, so this is like in the differential algebra, this is not equal signs. Those wiggles are just, up to compact operators. So up to very, very small operators. And then you can just see that the sign of the Dirac operator, so F is a sign of the Dirac operator, actually appears in the differential algebra. So this is absolutely highly degenerate, and this is that's the case. So I have no good interpretation. Why is it that? But it just comes out like that. So
Andrzej, I don't know if it's a good moment to ask you this question, but we can postpone it if you wish. Because now I see SEQ2 and my mind wanders in 2 different directions. One is how about other Waxman-Seuberman spheres? Is it somehow so much tied up to the dimension 3 of a sphere? Or if you want to stay in dimension 3, how about different deformations? I know, Matsumoto sphere, Kalov-Mate sphere, Heegaard sphere. You have
Yeah,
so many
okay.
different 3 spheres.
Yeah, so you see, I mean, the point is, I mean, why for SUQ2, this is quite easy because, again, there's a lot of techniques, a lot of tools that's been done. So basically, you see, I mean, as you can see, you know, computing this, I mean, all these functionals use residues. And computing these residues for a Dirac operator, a Fondé representation of algebra, I mean, basically, I mean, so if you just look at it, so those functionals, right, you see, okay, you see, this is W is the Wojcicki residue. So it's non-commutative residue. So basically what you use this one forms, you use representation of the one forms on a Hilbert space, which is, again, which is one of the things that's also quite difficult because you need to know the explicit representation. You need to use the explicit form of the Dirac operator, and you need to compute these residues. So this is, I don't know whether this is that's doable for the Weissman-Frost-Soberman spheres. I think this is doable for the Matsumoto spheres.
That's what I would suppose, yes.
Yeah, for the Matsumoto spheres, that would be doable, and that would be, I think, yeah, sort of a thing possible to do. Yeah.
Okay. Thank you so much.
But you see, I mean, for the Q deformation, I would say SUQ2 is the nicest example when one can use all these tools and get an answer. So the point is here, so the bottom line is, and this is still something preliminary from what I see, one could say,
and how
okay,
about Podlesh? How about Podlesh?
Podlesh is very difficult for a very simple reason, because this is not two-summable spectral triple. With the Dirac operator, it's sort of zero-summable. So I don't know how to, you know, bite the problem of those functionals for Podlesh. Maybe for the equatorial sphere, that would be more possible with the usual Dirac operator. So this is something also to look at. For the equatorial sphere, it might be actually interesting to look at, because then you can take the Dirac operator, which is two-summable. But for a moment, you know, SUQ2, you may say, you know, it's not very nice because, I mean, it's odd dimensional, but you know, this is the, so to say, a very nice sphere when you have really, I mean, quite interesting features that could be happening. So it's so, and I think, you know,
but you're not using its quantum group structure for it, just an algebra.
Yeah. The only thing is that, you know, of course, the Dirac operator is fully symmetric under the symmetry of the SUQ2. This is the equivariant Dirac operator. So that's the thing. Now it appears that when you look at it and when you compute some other functionals, but this is, again, I mean, I'm saying that this is preliminary result, and I mean, more needs to be checked and computed. It appears that the Einstein functional will not be proportional to the metric. So basically, I mean, you would have something like that, but this proportional. So basically, I mean, there would be, you get a metric for, say, two one-forms set number. You get also a number for the Einstein functional, but there won't be a universal proportionality constant. So this is something, you know, that could be different. I mean, that requires confirmation and further computation. So I think this is actually the case, but so it won't be like an Einstein manifold in this case. So it won't be that the Einstein functional is proportional to the metric functional, like it is in the classical S3. So, sorry, what is the main message of the talk? So first, using spectral functionals, one can define non-commutative formulation of what is a Ricci flow. So you just propose a Ricci flow is a flow, say, of the Dirac operator, d of t, such that there's a certain equation between the functionals, spectral functionals, which depend on this Dirac operator. Now, there are two things that needs to be mentioned. So first, you need to be sure that these spectral triples are torsion-free. Otherwise, it would be quite difficult. I mean, the classical picture would break down. So what happens for the almost commutative geometries where the torsion does not vanish, which is also something we showed with Ludwig? Well, then we need some other approach. So maybe we need to define some approach. What is the equivalent, or what is the idea of a Ricci flow, or something that replaces Ricci flow for geometries with torsion? I don't know
Andrzej, but I'm again confused by your vocabulary. What do you mean by the rigid formulations? Rigid formulation. What do you mean by the rigid formulation? Which formulation is it?
So the formulation of that means the rigid formulation means that the formulation that proposes the Ricci flow as the equation linking the dependence on T of spectral functionals. So d by dt. So that was the formula that I proposed.
Okay.
That's the phrase. But so, okay, so the torsion is a problem. So that's one of the things. Now, as I told you, open question. And the open question, and this is the challenge for all of you to try. So Ludwig, Adam, whoever is listening, examples. I mean, I told you, we are working on a couple of examples, but there could be more. I mean, like you Piotr mentioned, I mean, for example, Matsumoto spheres, so right, or even the four-dimensional spheres, four-dimensional quantum spheres. I mean, that there could be a lot of examples that can be studied. So then, looking, are there some non-trivial solutions for these spheres? So far, I mean, as I told you, I mean, I don't have any solution for the Ricci flow in this context for the SUQ2, but maybe there is something. So I don't know. Of course, there are general questions like the existence of solutions, even, the infinitesimal for small t or something like that. Now, I have absolutely no idea, I mean, at the moment, how to generalize it for example, the normalized Ricci flow, or to say something, I mean, what would be the change in the volume form, what will be changing in the volume? Now, there are some special solutions which are called solitons for the Ricci flow. If this is possibly in the non-commutative case, I have no idea. Now, the next thing is something that could be linked also to the spectral action. Namely, there are some special functionals that have been used by Perelman. They find actually this called Perelman functionals and Perelman's entropy that are defined for the Ricci flow. And they could be also used to reformulate the Ricci flow. So maybe that would be also another idea to have this approach in non-commutative framework.
And wait, just let me double check. So is it the technology he used to prove a Poincaré hypothesis?
Yeah. The Ricci flow was and those things were I mean, a little bit more, of course, than the Ricci flow alone, but yeah, Ricci flow was crucial in that. Yeah. Mm-hmm. And then, of course, there's one thing, namely, and this is something also relates to the question, posed. I mean, Ricci flow and Lorentzian geometry. I mean, of course, I mean, when you take something like 3+1 or n+1 geometry, this is not the same Ricci flow, but there are links between the Einstein equations in the Lorentzian geometry and the Ricci flow for the Riemannian geometry. So this is something that could help to approach Lorentzian non-commutative geometry. So this thing. And what I mentioned, I mean, there's an active area of studying Ricci flow and gravity. So this is also open here for all, say, mildly non-commutative modifications, I mean, including the standard model and gravity in the standard model. Okay, so that's all. And these are the concepts and ideas. Thank you.
Thank you very much indeed. Dziękujemy bardzo. Now let's continue with questions. Tomek, Adam, Ludwig.
In fact, I have several questions.
Go ahead.
So first of all, about this evolution of eigenvectors. So I remember that Thomas was asking about the evolution of the conformal structure of this Weil tensor. So somehow you don't control your eigenvalues, but you control eigenspaces, eigenvectors. Then you have the same structure of the corresponding to the spectral triple Fredholm modules. So maybe it is of some relevance. I don't know. Could you comment on it?
The point is, I mean, I think the Fredholm modules, so the K-homology class, should not change under that. Because I mean, the thing is, I mean, the evolution should be smooth. So topological things should not change. And I think that that's one of the results that the index doesn't change. I mean, it's one of the results that the index doesn't change.
Of course.
Under the,
Yeah. Okay, another question. How about this Ricci flow in the context of this finite dimensional algebra, which was relevant for the investigation of standard model in this model of Kohn and Lot, probably, and later Kohn and Shamsuddin, yes?
Yeah. I think, here, the relevant thing is torsion. So Ludwig, maybe you can comment on that. For the standard model, do we have torsion? I think yes.
Yes, and it is non-zero.
Yes. So this is the point.
Not only you have it, but also it is not zero.
Yeah. So there's torsion. And the point is that Einstein functional, I mean, ceases to be tensorial when you have geometries with torsion. And this is what we shown in a recent paper with Ludwig, Paweł, and Arek Bochniak. And the paper, I think, is already in Sigma. And so that requires certain amount of work, whether it's possible to formulate it for torsion. I don't know how to formulate it with torsion, because I mean, the standard Ricci flow, I mean, is for the metric. And I mean, then from the metric, you go to the Dirac operator with no torsion. And how to use torsion, how to see things with torsion, I have no idea. So that requires, some significant amount of work.
Okay, thank you.
Any comments on that, Ludwig?
Yes, the torsion. Okay, so the definition of Einstein tensor is problematic, as we know. We wrote actually impediment for Einstein functional in presence of torsion. We wrote a paper with ANDRZEJ and with Paweł and with Arek. Yeah, I think with Arek. Okay.
Yeah.
Other questions? Let's. I don't know. Maybe Tomek is before me. I don't know.
I have a question. Coming back to this problem of separating variation of the metric and variation of the spinorial structure.
Yeah.
So in your approach, you are varying the Dirac operator, as this variation came only from the variation of the Riemannian metric.
Yeah.
But then you are imposing some condition on spinors that this variation of the spinorial part is frozen. Is it consistent?
Maybe Tomek, maybe I don't know, ANDRZEJ, can I make a small historical remark about that? Okay. You agree?
Make, please.
So look, so I will, for any Riemannian manifold, you can write equation, which you can call in quotation mark Dirac equation. It uses only covariant derivative gifted with Clifford multiplications. Okay, so there are some matrices, matrix coefficient, partial differential equation, okay, and use Clifford multiplications and covariant derivative on any Riemannian manifold. In 1978, many years ago, two important physicists, Gary Gibbons and Chris Pope, tried to compute the index theorem on CP2, complex projective dimensional space. And they got index number 1/2.
Wow.
Okay.
That
so
sounds
it
like
was
a non-integer.
years, but mathematicians came and said, okay, your formal differential expression is an operator, but it doesn't act on spinors. It's a just formal differential expression, okay? There are no spinors on CP2. End, point of the story, okay?
Yeah.
But there are CP, and there are spin C spinors,
Spin
and
C,
you can modify and matter. But there are also manifolds which don't have even a spin C structure. So I mean, it's a problematic stuff, okay? So the equation which you write, I think is equation, this is a derivative with respect to some parameter of some formal differential, pseudo-differential operator in matrix coefficients, point. It did make sense. But if you want to include also spinors in this game, you have to be careful. You have to make dependence of spinors on the metric as well. Well,
Yeah,
which is very for arbitrary to arbitrary metrics, except for the conformal change of the metrics. Then you can identify different spaces of spinors for conformally related metrics. There's a very natural rescaling, the identification.
Yeah.
But you can identify spinor fields or sections for different arbitrary to different metrics. Point of the story.
Yeah. So I just wanted, to, so Ludwig is right. So basically, I mean, this is the funny thing in the original Bourguignon-Godeschon paper, there are actually two formulas and one uses psi, the other doesn't. So that's, can you see it?
Yeah, of course.
Yeah. So this is the main theorem of Bourguignon-Godeschon, and that's, I mean, the formula 21 uses psi, the formula 22, which is consequence of another theorem, doesn't. So, yeah.
So
Ludwig,
wait a moment.
please,
So
could you
this
please
means.
show that?
Sorry, but this means that this problem, this equation, this formalism, they are consistent only provided this Ricci flow is a conformal transformation of a metric.
In this case, you can make sense of the full equation, including spin or psi. By dt acts also.
Yeah. So this was my point, that otherwise you have to variate everything. Dirac operator and the spinor structure, the representation. Because the spinor representation is not, God-given. It's a choice, which is only compatible with the orthogonal structure. It's a choice of some hyperbolic plane in some tensor construction. There is no God-given spinor representation. It's always a choice, and this choice is very big, very ambiguous. So it's not clear to me how even variate Dirac operator in a way which is compatible with Riemannian metric.
Oh, what do you mean?
Make this variation consistent.
Well,
Thomas,
Thomas,
of course. Yeah.
You can variate. This is a kind of tensorial operator, except it doesn't act on spinors. That's the end of the story. It acts on some abstract Hilbert space. Okay.
Exactly.
No. Okay. You can create something like an element of the some vector field with values in the Clifford algebra. So this is the tensorial object. But once you start acting by this differential operator on anything, on some bundle, you need a representation of the Clifford algebra.
Yeah,
And
but
then
I
you
mean,
obtain, and then you obtain not such rigid constructions, allowing you to induce deformations or some change of operator purely from varying the metric. Because for spinors and the Clifford algebra, you have only compatibility. You cannot derive spinors purely from the Clifford algebra, which depends only on the metric.
I agree, absolutely, yes.
Yeah.
So there's big ambiguity here, and if you start changing something, this ambiguity changes even more. Because the compatibility between the Clifford algebra and spinors is very, very loose.
Yes, I think. Just let me make a comment about Thomas'
Go ahead.
question. Yeah, I mean, this is the issue you're addressing is just the main content of the.
Can you
this
do something
paper.
to your volume? I can barely hear you.
No.
Mhm.
Now, can you hear me?
Oh, yes, now I can hear.
Yes.
very good.
Okay. Yes, I mean, it's so here the main contribution of this paper is that so there is so of course the spinor representations varies with respect to the metric. So the point is that you move everything to the initial metric. So you are using a family of this unitary equivalence. Just pull back everything back to the initial metric. So that's the
Exactly.
yeah, that's what this paper is fighting for. That's the main difficulty of this variational problem is that you use one Hilbert space using the one associated
Exactly.
with the initial metric, and then there is a unitary equivalence. You just conjugate everything back to the initial metric. So that's
No, I cannot agree. I cannot agree,
Why?
because if you refer everything to this initial metric, you cannot change this connection. Okay,
You cannot change what?
connection,
Why?
because the relation between connection and the action of this connection on a vector bundle goes through a representation.
you don't change the connection.
And
You have
they have to go in the same time. You cannot freeze one and extend the connection by what rule? It doesn't
No,
make
you
sense.
don't extend the connection.
But this might be quite simpler. I mean, I think this is what Young is saying, and I mean what we used to with Ludwig a lot of time. I mean, for computing the Dirac operators. I mean, on the conformal rescale torus. So this is something like that. I mean, you have for each metric you have a Hilbert space of spinors.
Yeah.
This is the same Hilbert space in a way, because I mean all Hilbert spaces.
Yeah, but
are,
no.
Why not?
No, because this unitary equivalence of this is highly dependent on choices. You cannot fix what a standard
No, you don't change the
isomorphism
connection.
between
So
Hilbert spaces. These are
you just
completely
conjugate the
different.
Dirac operator. You don't change the
Exactly.
connection. You just basically say at metric GT sometime T, right? So then you have this corresponding like unitary transformations back to the initial Hilbert space. You just do the conjugation for this DT. DT is the Dirac operator at time T.
Yeah.
You don't change your connection. No. You just do the conjugation.
But you have to connect. No. But this was my point. You have to, if you variate this Dirac operator, you have to change your connection.
No, I don't vary. So we don't vary the Dirac. You have a family of Dirac operators. GT depends on the metric GT, right? So
yes.
So and then for each T, you conjugate back to the initial metric, and then
I don't
and then you
understand
do the
this.
variation at the initial metric. So in the same Hilbert space, then you can set up the variation of problem. So
I
otherwise,
don't understand this, the same Hilbert space. These Hilbert spaces, of course, they are isomorphic,
yes,
but it's not the same
Yeah.
Hilbert space.
yes, we use the unitary equivalence to move everything
Exactly.
back to the initial one, so that we
Yes,
can.
but
Yeah.
but then there's a problem. If you come back to the previous, you are changing the representation of the Levi-Civita connection on this. It is not the same Levi-Civita connection for both.
No, we don't need to worry. So first of all, we worry
We have
about
to worry.
operators.
We have to worry because the Dirac operator is a combination of the representation of this Clifford algebra and also the representation via spinor representation of the Levi-Civita connection. So both have to change. You cannot freeze one. And
basically we only vary. No, so okay, so once we have a family of matrix GT, okay, for each T, so you use the corresponding Levi-Civita connections to define this Dirac operator dt. Let's say it depends on your time. Okay,
it's not enough. It's not enough. This was one of my points. You don't have a canonical action of the Levi-Civita connection on spinors. You need a relation between the representation of the spin group and orthogonal group.
But Tomek, I mean, I don't understand what you're saying. I mean, if you have a metric, and if you choose the spin structure, so spinors, choose the bundle of spinors, then the Dirac operator is fixed. It doesn't depend on anything. I mean, if
you fixed what?
Spin structure.
Yes.
So you fix the spin structure, and then the Dirac operator is fixed when you have a metric.
Yeah, but if you change
it
the
doesn't
metric,
depend on anything. I mean, it's uniquely determined.
No, it's not true, because module acted on by this Dirac operator changes.
Yes, it's easier. So okay, so Thomas, so for each metric, so we have a spinor operator, right? dt, right? So depends on. Okay, so
acting on its own spinor bundle.
Yes, they act on different Hilbert spaces so that we cannot subtract them. So we cannot do variation. But for each dt, there is a unitary equivalence. There is a unitary operator when you conjugate with this Dirac operator with this unitary equivalence, and then we can move this operator back to the initial Hilbert space, on which we can do this variational you can subtract and take limits. So that's the
Okay, guys, I think that we begin to move in circles, and we cannot sort it out without the blackboard. So let's cut
then the variation of this Dirac is 0.
So we continue when we meet in person with Tomek.
Yeah, exactly. I mean, and let's see who is
at the blackboard. Yeah. Okay.
Yeah, because when we go into a loop and I see the same arguments over and over again, we need a blackboard to really decide what is right here. So let's stop. And anybody else having any other question? Ali?
Yes, I have a question about the formula. In the classical case, you computed the derivative of the volume form with respect to t, and we observed that the derivative is independent of t. So I would like to give a comment because it answers some of my previous questions. I always ask myself under what conditions we can have a periodic Ricci flow. And I understand that if the Euler characteristic is not 0, so we cannot have a periodic Ricci flow. So maybe is it a good question to ask for the Euler characteristic equal to 0? Can we always have a Riemannian metric for which the Ricci flow is periodic?
I don't think they are. You see, that's a good question, but I don't know whether there are periodic Ricci flows. Because I mean,
What kind of
the Ricci.
abstraction would appear?
Sorry?
What kind of abstraction would appear for existence of a periodic? Today, I understand the Euler characteristic is an abstraction.
Yeah, but this is, I mean, this is just for surfaces. So of course, I mean, if Euler characteristic, I mean, is non-zero, then it's either grows or the volume either grows or goes to zero. But anyway, I don't know whether the periodic Ricci flow is possible. I haven't seen anything haven't seen any solutions which are periodic, because this is a type of heat equation. The heat equation doesn't have, I mean, generally, I mean, heat equation of the heat type doesn't have periodic solutions. So that's, I don't know whether there are.
Okay.
Yes. Okay. Okay. Thank you, and thank
Joe?
you for your great talk.
Do you have a question? Joe, hello. Do you have a... No. Okay, no question. So if there are no other questions, let me ask a kind of provocative, not really a question, but a thought. How about using your non-commutative Ricci flow to prove a non-commutative Poincare hypothesis?
Very good.
I'm just provoking you, so you know. I'm wondering what your opinion is. You know.
And the opinion is that, you know, one of the techniques that are used apart from the Ricci flow are related to surgery, as far as I remember. And the thing is, I mean, if you know what would be sort of surgery for non-commutative objects, that would be great.
Pullbacks of sister algebras.
Yeah, the thing is, I mean, yes, sister algebras are very nice, but I mean, you need to, I think for the manifolds, you need to work with smooth things.
Yeah, right. Yes.
So that would be But I think, you know, generally, I mean, my motivation was to use the spectral functionals to see what is possible, and amazingly, a lot of things are possible. So that's you know, there's a challenge. I mean, what could be used? I mean, some things could be used. I mean, it's sort of a challenge, you know, to see, for example, I mean, what are the possible metrics? So for the non-commutative tori, for example. So what are the possible Dirac operators? So maybe then the Ricci flow could somehow say something, whether there are some special points or some flows that go to certain metrics. I don't know, but you know, that could be used, you know, to study more geometry.
Tomek, wait a second. Just let me finish here. I want to somehow see your take-home message. So you are advocating your approach with Ludwig by this functionals and Wojcicki residue.
Yeah.
But did I confuse something, or did you at a certain moment show us a case where it was useless? You got 0 equal to 0.
Yeah. This is the well, useless or okay, not contradictory at least. The point is that non-commutative world is very very funny. So if you go to the commutant of an algebra, so classically commutant of the algebra includes the algebra. The point is, when you go non-commutative, like for the irrational torus, I mean, the only intersection are the constants, right? Yeah. It's complex numbers. So it's a completely different object. So for this completely different object, and also, I mean, this is only in 2 dimensions, I mean, it somehow like detaches. So the interesting thing, and this is something, you know, working on with students, is to look at the intermediate case. When you have some things in the commutant which is apart, but not much. So the rational non-commutative torus. So the non-commutative, I mean, this shows that the non-commutativity, I mean, is somehow special. because I mean those things in the commutant they somehow detach. That's one thing, and of course I mean this is the limitation of the definition of the Ricci flow by the spectral functionals, because the spectral functionals they use a little bit more than the metric alone. You use it like the density. And then it changes the properties of rescaling and of conformal rescaling. And this is the reason, I mean, those things detach. And also those factors appear in the differential forms, which is absolutely, I mean, the only approach to differential forms we have only to the Dirac operator. And in a way, the metric is in the Dirac operator. So it is in the differential forms. So this is the game. Unfortunately, this is so.
But if you were to put it very succinctly, saying, okay, so there was another approach to Ricci flow, but you propose something better, and in at least this regime, under these assumptions, you have a better paradigm. Would you be able to specify it like this? So what are the assumptions again? So this is related to torsion, I remember, right? You want
the assumptions are that you have a finitely summable spectral triple.
Mm-hmm.
And the Dirac operator is torsion free.
Okay.
And then, so I mean, then you can define the non-commutative Ricci flow as the flow of the Dirac operators such that they are torsion free for each t, and the spectral functionals satisfy this equation for all differential forms.
Okay, excellent. And in this regime, the other approach wouldn't work?
I have no idea. Because the
I
other
remember.
approach,
The problem with them is that they're non-computable.
exactly.
Okay. I'm happy. I'm completely happy. Now I can give you to Tomek to further torment you.
No. I have a little comment about your question.
Mine.
Which was very, very interesting about topology and all this differential geometry, because the classical Perelman's proof of the Poincaré conjecture is based on a very simple fact that in dimension 3 there are no exotic smooth structures. So there is only one smooth structure on 3. And therefore, differential geometry is so effective in topology. Okay, so now the question here could be,
what is the smooth structure?
Yeah, how many exotic differential non-commutative differential geometries you can have in every single example?
Very good question. Try with, I mean, this is a challenge, you know, to define what would be the definition of a smooth structure. Maybe
in the sense of cone, for instance.
Sorry?
In the sense of cone.
But what does it mean in the sense of cone? I mean, well, you can define, I mean, it would be like a smooth structure. I mean, you choose a certain smooth subalgebra of a system algebra and so on and so forth. But the point is, it would be good to have an example of a, so to say, spectral triple or whatever, spectral geometry for a exotic smooth structure, classical. And I haven't seen anything like that.
I propose Q-deformed 7-sphere, Andrzej, okay?
But which sphere?
7-sphere, Q-deformed.
Max von Soibelmann?
Why?
Because on S7 we have
Briscoe spheres. Four-dimensional seven-dimensional Briscoe spheres, which are responsible for non.
No, but Ludwig, what I was talking not about Q-deformed things. I was talking about a classical.
Classical, yes.
So take a manifold with an exotic smooth structure and construct something what would be a spectral triple for this exotic structure.
Yeah.
For instance, the Briscoe sphere, 7-sphere.
Yeah. I have no idea, and I haven't seen anything like that. And this is an interesting point, because I mean, if you look at the Kohn reconstruction theorem, right? That would be now, okay, reconstructing, you take the Dirac operator and it reconstructs the smooth algebra. So how do we know which smooth structure we get?
Yeah.
And this is you know, a challenge. I don't know anything about it.
And this is a good point to wind it up. So let us thank ANDRZEJ again. Thank you so much.
Thank you.
Thank you for
And
your
let me
time.
stop the recording.
And see you next week.